final question. Right, so this was the other 2019, so something happened, I forget what happened, but they needed 2 versions of the exam. So this is the last question of the exam, I think on the West Coast. So here we go. Okay, so this is clearly an energy problem. We're gonna probably have some sort of sum of forces to see if it makes it here. So sum of forces in the radial direction is equal to mv squared over r. Okay, let's see. Rotational inertia of, okay. Right, of all these things is some constant b. Right, we know that. Okay, hoops, yes, great. Hoops would be 1, disks would be half, fine. B, right. Okay, turn the value of b for a partially hollowed out sphere. Oh, interesting, like a shell. Students use loop track of, thank God, we don't have to worry about that. Okay, great. Derive an expression for the minimum speed of the center of mass will allow. Oh, okay. This solid question. So what we're going to do is we're going to do UG is equal to 0 down here. V min at A. Let's just do this first. So here's the object at A. Fn, Fg, sum of forces in the radial direction is equal to MAR. And so this is Fn plus Fg is equal to mv squared over r. We're going to take the limit. As Fn goes to 0, that's v goes to v min. So mg equals mv min at a squared over r. Masses cancel. So v min at a has to be equal to radical g capital R, right? Because that's what that says. Now, energy at A is equal to energy at P, the beginning. Work non-conserved is equal to 0. Here, I know it's got to have UG at A plus KER at A plus KET at A is equal to just UG at point P. Great. So UG at A is mg2r. KER is 1/2. The I is that generic BM little r squared. And this is omega. I know I'm going to put in VCOM over R, right, eventually. So let's get in terms of that because I know that I have a VCOM expression there, plus 1/2 mv at these should be a point A squared is equal to mgh. All right, let's clean this up. 2mgr. Actually, let's cancel some m's before I do that. So 2gr plus, here I'm going to have half b r squared. Actually, the r squared and the r is going to cancel, so we get rid of that. VCOM squared, so that's just going to be gr plus 1/2, and then this just becomes gr from above is equal to gh. Oh, look at that, all the g's canceled. So, what do I have? 2 capital R plus 1/2 b capital R plus half capital R equals h, right? So let's make a nicer expression for that. 5/2 plus 1/2 b R is equal to h. All right, cool. Great. Boom. Students perform, they get this, okay. So suppose the sphere is released from rest at some point P and rolls without slipping. Hold on a second. Derive an expression for the, that's part A and this is part B. I just did them both. All right, awesome. Okay, let me collect the data on the grid below, plot H versus B. This is just like grunt work. I don't know why, like they think it's useful to make you graph things. 0.5, 1. What are we going up by here? Going up by 0.4s. 0.4, 0.8, 1.2. Right? Why not? Actually, no, 0.3s. Silly. 0.9, 1.2. Okay, great. So B is 0.4, so it's here. you get 8. Oh my god, all the h's are okay, whatever. 0.4, 1.0. This is going to be ridiculous. All right, let's see if we can get some differentiation. Ugh, they want us to do a break graph? Oh, that's just appalling. All right, let's say this is 1, 1.05, 1.1, 1.15, and this is 1.2. Oh, sorry. Should never do graphs that don't start at 0, 0. That's just terrible. Anyway, we want to see what's going on here. 0.67, so that's 0.6, 0.7, 0.67, 0.3, and then we go down 0.5, it's 1.1, and then 1 is 0.2. Okay. Yeah, so draw best fit. Great. That's terrible. Soon repeat the experiment to find the partially hollow. So 1.6. So we're just going to interpolate across here and go down to there. Great, so that is 0.6, 0.7, it's literally 0.8. Okay, 0.8, that's my answer. Okay, calculate R, the radius of the loop then. Okay, so let's use, I mean, this is just busy work. What the hell? 1.16 meters is equal to 5/2 plus 1/2 times 0.8 R. All right. So this is 1.16 divided by, this is 2.5 and then 0.4, 2.9 is equal to R. So whatever that number is. Like, the physics was the first two parts of this, and the rest of this is just like nonsense. Hopefully F is more interesting. Okay. Oh, yes, it is. Little radius r of the rolling sphere is assumed to be much smaller than r. If radius r is not negligible, would the value of the minimum release height be greater, less, or the same? Ooh, that's a great question. So let's go back to our expression here about what we have here. So this would be the y initial, and this would be the height at there. And so, what would happen then if it is not true? Well, what terms would change? Well, certainly this term would change because it wouldn't be, we would have a v min would be radical g r minus little r, whatever that is. And this height here would not be 2r, and we probably wouldn't be measuring UG from the ground because, well, let's say we just still continue to measure UG from the ground. So that would mean that this term would not be 2r, it would be 2r minus little r. Okay, and so then we would have r minus little r here, and so we want to know, would h be bigger, smaller, whatnot? Look, all the terms here pick up an r minus something, and so that means h is smaller. So there it is, it's less because r minus little r goes into all the EA terms, so EA is less. Okay, great, and there you go.